All right, so where did we leave off? Oh, I know where we left off. We left off at Pear Deck. Let's start. We got a lot of thinking to do. So I'm going to give you guys 30 seconds on this because this is a problem that we did last week. Yes.
The last question, I did some of it, but I still have a few questions because I still have to look. I just got into haiku, so
Okay.
I need to go through everything. So could I
Sure.
do it in, like,
Yeah, just hand it in whenever.
Okay.
All right, consider the line labeled B in the V versus T plot. How does the speed change with time? And I need to make, can you stay after school today? 20 seconds. I guess you better start. My feeling is that you don't necessarily, if you're logged in by the second question, that's perfectly fine. Time! All right, so what do we got? What happens to the speed? Anyone? Yes. That is correct. The speed will decrease until v equals 0, and then it will increase as the velocity turns more negative. All right. So, man, why not? Let's do this. Rank the magnitude of the accelerations. I'll give you a minute. Fifteen seconds. 10, 9, Casey, Ariana, Chris, Emily, Powers, nice smiley face, Samantha, 5, 4, 3, who needs more time? Say more time.
Theme song, Mr. Khalil. See if you can name the movie. And boom, boom. How's it go? Boom, 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 boom. It's an old one. It's probably
Oh, I'm terrible at pop culture references.
The Exodus.
Oh, good stuff.
Yeah. The Exodus is underway.
Oh, nice. Is that from here or in general?
In general.
Nice.
I'm up from 21 to 26.
Oh, they're coming. They're coming your way.
Yeah. Charlton Heston. Is he Charlton Heston?
Well, what we have here is the wheat.
All right.
We have the wheat left. No one got that. So, you guys are the wheat. So, anyhow, so what do you got? How are you going to determine the accelerations? Yes. That's right. And what do you see? A lot of parallel lines. Meaning? That's right. Which lines are parallel? That's right. And the magnitudes of each of those are equal. The only one that's not is, and it's greater than them all. That's right. So there you have it. Now we get to more interesting questions like this. All right, so I don't think anyone can read this. I'll read it to you. It says, a student obtains a graph of an object's velocity versus time, and then draws the graph of the acceleration versus time for the same interval. So that's the graph. That's the v versus t, and this is his drawing of a versus t. You have to rip apart his drawing. In other words, you have to tell him precisely why he doesn't know what he's talking about. And also what's good about it. Like, there may be some parts of it that are correct. Identify what's correct and what's incorrect. I'll give you a minute. A lot of time to think about it. I don't know. Does it? I think it tells you to draw what the right one is. Is that the prompt, to draw the right one? All right, so let's see where we're at. So now here's the question. Is the overall structure of this graph kind of right? And the answer is yes. The overall structure of this graph is kind of right. And what do I mean by that? Yes. That's right. The acceleration is negative in that first leg. If we divide this up into 4 legs, acceleration is negative in this first leg. And the acceleration is positive in this third leg. In the second and fourth, the acceleration is 0. So what's wrong? Yes? Technically, no. You can. That's a minor issue. What's your name again? Go ahead.
Will the acceleration be positive?
The acceleration should be positive here. In other words, this is a positive acceleration. Slope is greater than 0. This is a negative acceleration. Yes?
Well, the slope is a lesser slope here than it is here, so that should actually be higher than the first one.
That is correct. So everybody follow this. If you look at the size of this, this should be taller than this is, because the magnitude of the acceleration is larger for that second accelerated segment than it is for the first. So I think I have it written out here. Now this is, by the way, see this style of question? This is very much an AP1 style question. Notice it asks you to identify what's both good, what's correct, and what's incorrect. This is actually a very difficult skill to develop. Usually I would say it's more of a second-year skill, but they put it on the AP1 exam. Not easy. So this is the correct graph right here. Notice it's shallower here and much more elevated here in terms of magnitudes. I'm going to be publishing these on Haiku, so it's not necessary for you to draw all these out. All right. An object moves along the x-axis with a constant acceleration. The initial position, x0, is positive. The initial velocity is negative. And the acceleration is positive. Which is the correct v versus t graph? 1 minute. I'll even give you 45 seconds. You should be able to answer this in 45 seconds easily. $15 seconds. Falvo. Cecil. Powers. Five, 4, 3, 2, time. Lock the responses. Show the responses. All right, so we've got basically an even split between B and D. So let's actually go and see each of the reasonings. So who here picked D? Okay, who here wants to justify their choice for D? Go ahead.
I think he's totally wrong, but I just because the initial position of x is positive, and since velocity is negative, would that mean that this should also be negative?
For which graph? Correct. What type of graph is this? Very good. So, it's a velocity versus time graph. So, right off the bat, what's going to be extraneous information here? Yes. That's right. The initial position is actually extraneous information. It doesn't help you at all. So now let's actually go and reflect on this. What we have is that the initial velocity is negative, which means on a velocity time graph, it means it starts where? Below the axis. And the acceleration is positive, which means what? The slope is positive. So therefore, which one starts with a below the axis and has a positive slope? B. So you can see that these questions flesh out all the conceptual errors that will happen. This is a position versus time graph. So the position versus time graph of the motion of a particle. Of the 4 points P, Q, R, and S, the velocity is greatest at what point? It's the position versus time graph. At which point is the velocity greatest? 10 seconds. So you guys are in good shape. This is good. So Emily, all right. So we've got, I'll lock it. I'll show the responses. Yet again, 50-50, or close to 50-50. So let's actually flesh out who's right and who's wrong. So who wants to volunteer their answers? Yes.
I said B because it's the average velocity is equal to slope.
The what's
The average velocity is equal to the initial velocity. Instantaneous.
The instantaneous velocity is the slope at p, okay?
And that's the greatest slope, and r would be a negative slope.
Boom. So those who said C, what quantity were they thinking? The magnitude, which is the speed. So R has the greatest speed, but P has the greatest velocity, where greatest means most positive. Because at point R, it has a negative velocity. And so this is the answer to the previous question. It's clear that it's at point R. The greatest speed is at point R. So now, okay, this is a little tougher. This is a position time graph. Of the 4 points, P, Q, R, and S, which one has the greatest acceleration? You're like, huh? How are you going to infer the acceleration from a position time graph? I'll give you guys a minute and a half on this, because this requires some thought. All right, I'll give you a hint. Here's a hint. Acceleration is final velocity minus initial velocity over the change in time. The change in time is always positive. That's the hint. All right. Time to make your decisions. 10 seconds. You guys are good. You guys are real good. Okay. Maybe. Actually, some of you guys are good. 5, 4, 3, 2, time. Lock those responses. Show you the distribution. All right. So, a lot of people think it's point A, meaning that's point P. And I'll tell you, this is not an easy question. In order to answer it, what we have to do is we have to look locally around each of these points. What do I mean? What I mean is this. I'm going to draw this graph. I'll use chalk, God forbid. No, I won't use chalk. Yes, I will. Get over here. All right. So, position, time. What does this look like? This looks like this. All right. That looks roughly about right, right? So I take P, and I take Q. Okay? And right before P, what does the instantaneous velocity look like? Right before P. Looks like the tangent of this, right? So this is VI. Right after P, it's basically the same thing. So this is VF. The slope of those is VI and VF. So what's that change going to be, roughly? 0. In other words, the acceleration around P is roughly 0. Now let's take a look at R. What do you think it'll be around R? Yes. Correct. It'll also be around 0 at R. This is R. The tangent at a point right before R is going to be that line, and right after R is going to be this line. So the accelerations are going to be the change in the slope of those tangent lines. I think that's kind of crazy, right? So now let's take a look at the two inflection points. So the one inflection point is Q, and the other one is P. So I'll take, let's say, this point. The tangent line looks like this, and that is a positive or a negative slope? Positive. So VI is then greater than 0. That was terrible. And VF was less than 0. So therefore, the change in V is going to be what? Is going to be negative. Because the final velocity is negative, so negative minus initial, the initial is negative, negative minus negative is negative. Excuse me, negative minus positive is negative. So delta V at point Q is less than 0. Now let's take a look at point S. At point S, you look at a point right before it, and where's the slope directed? Down, which is? Here's VI. You look at a point to the right, and the slope is directed up. There's VF. So we have VF is greater than 0. VI is less than 0. So therefore, delta V at point S is going to be a number greater than 0 minus a number less than 0. So that's going to be a number greater than 0. So therefore, the answer based on this reasoning is point S. Now here's a question. Which one has a larger magnitude? Point S or point Q? Yes. Correct. Point S has a greater magnitude, which tells you that if you want to know the acceleration on a position time graph, you look at something called the concavity. How concave something is. And as you can see, which one is more concave? S or Q? In other words, which one has a tighter turn? S or Q? S. So the magnitude of the acceleration is greater than S, and the direction of the acceleration is positive. Obvious or not obvious? That's not obvious. Come on now. Come on, guys. Oh, this is obvious. Give yourselves credit. All right. Now we get to the really good questions. Because that was a really good question. And this is probably just as good. This is the velocity versus time graph. Which of the following descriptions of the motion is the most accurate? I'll give you 2 minutes. Well, I'll give you a minute. You might be able to reason this in a minute. Powers! Talk it over. Talk it over. Talk it over. I wouldn't be telling you to talk it over if I didn't think that you needed to talk it over. Ah! All right. Another 10 seconds. Who is calling me? This is my joke phone. All right. 5, 4, 3, 2, 1. Time. All right. You guys are in good shape. You're in really good shape. It shows you that you're really getting this. Who wants to explain it? Go ahead, Kramer.
So, this is the next look at velocity over time. Since the initial point is higher on x value than y value than the final point, is slowing down. So that was A or B. And then I just kind of broke up the graph into two halves. Like the first half has a greater slope than the second half, where it starts leveling out, so then it's at increasing rates. Okay?
Correct. Preserve that brain of yours, though. He's leaning back on his chair. And very easily, the back of our heads are very soft. The type of impulse that would be required to give him a concussion wouldn't be much. So, he's completely correct, though. If you look, the velocity is going to 0, which means the speed's decreasing. Okay? Or it's slowing down. And if you look at the slope, it's becoming more and more shallow, which means the acceleration is approaching 0. So, all right. Are you guys ready for this? I'd say maybe not, because I need to actually introduce some concepts right now. So, what I'm going to do is I'm going to state without proof the following. I'm going to write it down and just state it without proof. And of course, your reaction should be, oh, Mr. Cleo, are you kidding me? What are you doing? You can't state something without proof. And the answer to that, of course, is I put the proof in a video for you to watch for homework. So, I just don't want to necessarily use the class time to go over the proof. One, because it would be difficult for you guys to understand it, but not terribly difficult. Watch the video. It'll be posted tonight. So, the proofs are as follows, or the two statements are as follows. One, I hate stating things without proof. I'm sure this is pretty normal for you guys, but if something's not proven to you, it's not real knowledge. It's pseudo-knowledge. It's memorized chunks of information. Anyhow. So, first one is on a velocity time graph. The area between the curve and the t-axis is a positive displacement. The area between the curve above the t-axis is a positive above the t-axis is a positive displacement. In other words, it's equal to delta x. And therefore, below the t-axis would represent a? Correct. The area between the curve below the t-axis is a negative displacement. I'm sure you saw this in your reading, correct? So what this means is if I have a velocity time graph, consider the following v versus t graph. I don't know. This is v, this is t. That this area, say this is t equals 0, this is t equals 1, and this is t equals 2. This area in the shaded region is equal to x of 1 minus x of 0. This area is equal to x of 2 minus x of 1. In the top case, right, in the case of this area, this difference is going to be what? Greater than or equal to, yes, 0. In this case, this is going to be less than or equal to 0. So the displacement is the area between the curve and the t-axis on a velocity versus time graph. So watch this, and you'll see. So how did I write that? That was, okay. The area between the curve or you could say between the curve A of t above the t-axis between the curve above the t-axis on an acceleration versus time graph represents what? Anyone? A positive change in velocity. Likewise, the area below the t-axis between the curve of an A versus t graph would represent a negative change in velocity. And what you'll see in the proof tonight is that all these are consequences of the fact that the delta of anything is a telescoping sum. So, any questions on this? Seriously, any questions? All right, now you guys are ready for the kinematic equations. So uniform accelerated motion. You have two kinematic equations that are the result of uniform accelerated motion. What does uniform accelerated motion mean? Anyone? Uniform accelerated motion means A is constant. So your kinematic equations. And I'm going to prove them all to you. Whatever. So, the first one is what I call the first kinematic equation. Well, there's the kind of sub-ones that I don't really think are true kinematic equations. For instance, the one that I had already proven, that v of t is equal to v of 0 plus at. We'd already shown that in the last class. In other words, that your velocity function in the case of uniform accelerated motion is, what is it? It's a linear function of time. Similarly, if I were to ask you guys a very basic question, so basic that I think a lot of you might not get it. And then when you see the answer, you're like, oh, that's obvious. If I have linear accelerated motion, what does that look like on a v versus t graph for positive acceleration? It looks like a line, right? Where do you want to start, above the t-axis or below? I don't care. Pick one. Start above. It's a false choice. So call this point vi, and then call this point vf. And so now the question is, so here, boom, boom. Here's a question. What's the average velocity? Talk to each other. Spend a minute. Because realize what I'm really asking is, what is the average value of something along a line? What is the average value of something along a line? It's not the slope. Definitely not the slope. Yes? Very good. What's your name? Natalie, very, very good. It's the midpoint. If you have a line, where is the mean along that line? Or where does it take the average value? It's going to be at the midpoint. So in other words, v bar, in the case of accelerated motion, is equal to what? What is the midpoint between vi and vf? Vf plus vi. You said vf plus?
No,
vi plus?
and then VF minus VI. And then this last word.
Is that correct? And the answer is yes. But that's also equal to vf plus vi over 2. Those two are equivalent. To show that, what do? I write this as vi, 2vi over 2. Right? And I add all those other things. What am I left with? 2vi minus vi is simply just vi. So it's just vi plus vf over 2. Strong memory. So I think that was an equation that you were given at some point. So the average velocity is the midpoint between 2 points in time. So what would that look like in functional notation? That would look like v bar is equal to v of t minus plus v of 0 over 2, midpoint. Here's a question. $1,000,000 question, which is still a lot of money. At what time does it take its midpoint? At what time in uniform accelerated motion is the average velocity achieved over an interval? Meaning what point in time? The midpoint. In other words, v, the instantaneous velocity, that is not the instantaneous velocity at the midpoint in time equals the average velocity over the entire time interval. Equals the average velocity over the entire time interval. So these are the trivial, or maybe not so trivial, consequences of uniformly accelerated motion. The kinematic equations, which are the really non-trivial ones, are as follows. These are important, there's no doubt. They're important, we're going to use them. But the non-trivial kinematic equations, I guess neither of those are trivial either, are what I call the first kinematic equation. First kinematic equation. And it says that the change in position is equal to the initial velocity times time, or maybe I'll be even formal. It's equal to v at ti times delta t plus 1/2 a times delta t squared. And realize delta x means what? X at tf minus x at ti. Usually, this will take on a simpler form. We say let ti equal 0, let tf equal, and therefore, what would this look like? You would have x of t minus x of equals, what's v of ti? V of, yes? Ti is 0, so that's v of 0 times delta t is simply going to be t plus 1/2 at squared. So that's one form you'll see it in. Another form you'll see is just this. Delta x equals vit plus 1/2 AT squared. All these are equivalent. All of those are equivalent. Sometimes you'll see D equals VIT plus 1/2 AT squared. They all mean the same exact thing. Now let's prove it. So this is the first kinematic equation.